Hello everyone. In the last lesson, we looked at the intersection of a line and a plane, and now we're going to start moving up to intersections of planes. Okay, we're going to start with 2, and over the course of the week, we're going to build up to 3. Okay, and we're starting with 2 because the intersection of 2 planes in 3-dimensional space is kind of similar to doing the intersections of 2 lines in 2-dimensional space. Okay, so we're going to flip over to GeoGebra for a second here just to show what the cases are, and we'll summarize it quickly here. Okay, so here's a plane in 3-dimensional space. Okay, so again, this is similar to lines in 2 space. So most of the time, if I put some other plane on here, it's going to intersect this. Okay, but it's going to intersect it. Let's see, find where they intersect. Back up. There we go. Okay, so you can see where they cross each other here. There's a good view of it right there. Okay, there's the seam right here between the 2 planes. Okay, so when they meet in a line. Okay, that's what's going on. They meet in a line when they cross, right? When they're not going the same direction, you can see that from different angles here. There's a seam. Okay, that's where they meet. Okay, so that's one possibility, is they meet in a line. Okay, and again, that's like in 2D when they meet in a point. In 3D, if they are parallel to each other, okay, then they have no intersection. So they look something like this. Okay, like your favorite sandwich cookie, right? You know, the cream filling in here somewhere, right? They never touch. Okay, so they might not intersect at all. Okay, and that's the same as the parallel lines in the 2-dimensional case. Okay, so the third case in 2D is when you really have the same line twice. Okay, and it's same in 3D. If I try to trick you and give you the same equation of a plane twice, then they have infinite intersections. Okay, so those are the 3 cases here, right? One is that they could intersect in a line, so they're going different ways. Okay. Second one is they are parallel and they're distinct, so they're parallel to each other, but they do not cross. Okay. And third case is parallel and coincident. They are parallel and they are actually the same plane twice. Okay, so when we go to solve these, definitely the easiest way to do this is with the scalar equation of the plane, just like we would use the scalar equation of a line in 2D to solve that situation. Okay, and in cases 2 and 3, right, the tip-off that they're going to be parallel is that the normals will be scalar multiples, right, because the normals will also be parallel, right? If that's the normal of plane 1, right, and this is the normal of the other plane, they have to be going the same direction. Same in this case here. Okay, so this is going to be a fairly short note. I'm just going to go through a couple examples here of what that looks like. Okay, so determine the intersection of this plane here, okay, pi 1, and we'll do it with these 3 different planes and see what the algebra looks like. Okay, and these are the same 3 planes that I demoed on GeoGebra a moment ago. Okay, so I'm going to write out my plane 1 again. 2x minus 3y plus z minus 6 equals 0. Okay, and plane number 2 is 4x minus 6y plus 2z minus 12 is equal to 0. Okay, so first thing I'm going to quickly check my normals. So my first normal is equal to 2, negative 3, 1. Okay, and my second normal is 4, negative 6, and 2. Okay, and having a look at those, right, this one is just double the first one, so the normals are parallel. So either these planes are parallel and they don't touch, or they're really the same plane twice. Okay, and if you looked ahead a little bit at that last coordinate, okay, you can see that's also double. So yeah, this is going to be the same plane twice, but we're still going to go ahead and solve it algebraically. The way we're going to approach this is by using elimination. I'm going to try to knock out variables. Okay, so just like I noted it was double, okay, let's double that first equation. So pi 1 times 2. Okay, it would give me 4x minus 6y plus 2z minus 12 equals 0. Okay, and my second plane is 4x minus 6y plus 2z minus 12 equals 0. Okay, so now I go to eliminate. I'm going to subtract the equations. So my x's cancel, my y's cancel, my z's cancel, my 12 cancels. So I have 0 equals 0. Okay, but we've seen that before. Right, 0 equals 0 means we have, therefore, there are infinitely many solutions. Pardon my sloppy writing. Okay, and so this is the same plane twice. Same plane twice. Okay. So for B, we'll just do this all over again. So my first plane was 2x minus 3y plus z minus 6 is equal to 0. Okay, and my second plane, pi 2, was, pardon me, 4x minus 6y plus 2z minus 7 is equal to 0. Okay, these planes have the same normals as before, right? My first plane's normal is 2, negative 3, and 1. And my second plane's normal is 4, negative 6, and 2. Okay, now when I look at these coordinates, those are not scalar multiples of each other. Okay, but again, we'll go through the algebra just to show how it works. So I multiply the first equation by 2 again. So I have 4x minus 6y plus z minus 12 equals 0. And I have pi 2 is 4x minus 6y plus 2z minus 7 equals 0. So when I eliminate that, my x's cancel, my y's cancel, my z's cancel, because that's supposed to be a 2. And then negative 12 take away negative 7 is negative 5 equals 0. Okay, so this is impossible. So that means there are no solutions. Parallel and distinct. Okay, I guess that previous one I should have called it parallel and coincidence. All right, so third case. So again, my first plane, this is C. Okay, again, I had my first plane is 2x minus 3y plus z minus 6 equals 0. My second plane, x minus 3y plus 2z, x minus 3y plus 2z minus 18 equals 0. Okay, we have a quick look at the normals. So my first normal, again, is 2, negative 3, 1. And my second normal is 1, negative 3, 2. These are definitely not scalar multiples because for my y coordinate, I would be multiplying by 1, and for everything else, they change. Okay, so they're not parallel. They'll definitely intersect in a line. Okay, so this part is a little bit new, right? How do I end up with the equation of a line when I try to do the intersection? Well, we'll do the same process. Okay, we're going to try elimination here. It doesn't matter which variable, but for the sake of consistency, I'm going to eliminate x. Okay, I know you don't have to, but I'm going to try to eliminate x here. Okay, so that means I would have to multiply my second equation. So this was pi 4 down here. Okay, I'm going to leave my first equation alone for elimination. So 2x minus 3y plus z minus 6 equals 0. Okay, I'm going to multiply my second plane by 2. So I get 2x minus 6y plus 4z minus 36 equals 0. Okay, now I go to eliminate. So my choices cancel. 3 minus negative 6 is positive 3. 1 take away 4 is negative 3. Negative 6, that would be plus 30, and that equals 0. Okay, so this is where it gets new, I guess, compared to previous stuff. Okay, I'm going to solve this equation. I have nothing else to work with, so I'm going to solve this equation for y. Okay, so I have 3y equals 3z minus 30. Okay, divide everything by 3. Y equals z take away 10. Okay. So here's a little trick of how we're going to turn this into the equation of a line. Okay, this kind of looks like a parameter, right? Y equals z minus 10. So we take a step and we're going to say let z equal t. So because I know there's multiple answers, I'm just going to let one of my variables become the parameter. Okay, so if I let z equals t equal t, that means y equals, and I'm going to rearrange this so it looks in the right form, is negative 10 plus t. Okay, that's my second parameter. And now I need to solve for x, so I need to go back into one of my equations. Doesn't really matter. Let's take that first one and solve it for x. Okay, so again, my equation pi 1 was 2x minus 3y plus z minus 6 equals 0. So now I'll sub in. I have 2x minus 3 times negative 10 plus t. Okay, I'm letting z equal t minus 6 equals 0. So 2x plus 30 t plus t minus 6 equals 0. Let's see, it's 2x equals negative 3 plus 1 is 2, and then I bring it over. I'm going to have 2t. And then I have 30 take away 6 is 24. Bring it over, that's negative 24. So x equals negative 12 plus t. Okay, so in summary, my x-coordinate is x equals 12 plus t. Okay, my y-coordinate was, I believe that was negative 10. Yep. Negative 10 plus t, and z is equal to t. So there's the parametric form of the equation of the line. That is where these two things cross. Okay. And now let's just write that in vector form. My other form for this, my line x, y, z, equal to my point is negative 12, negative 10, 0, plus my parameter is t, the vector is 1, 1, 1. Okay, and there's the equation of the line. Okay, as just a quick little check here, I went back to GeoGebra, okay, and I zoomed my planes out of it here. Again, you can see where that seam is, where they cross, and if I put on the line, it's lying right where that seam is. Okay, so that's the line where the two things cross. Pretty neat. Okay, so that is all for this lesson. Okay, so again, your three cases are take an intersection line, not intersect at all, will be the same plane twice. That's when they're coincident. Okay, so there's the practice. And over the next few days, we'll get into solving systems of three planes. Thanks for watching, and we'll see you next time.